Hello, everyone. Welcome back. Thanks for joining for another session of Particle Physics for Teachers. So I'm really excited today to be turning things over to Dave Fish at the Perimeter Institute for Theoretical Physics. A couple of you have already been on Perimeter programs. You might recognize Dave if that's the case, because he's been there since the start. Is that right, Dave? Like on and off as a teacher in residence and now long-term?
Yeah.
And so, as I've mentioned before, Perimeter is by far my favorite, or what I consider the best place for any kind of modern physics resource, partly because of how they develop things, which Dave is a big part of that. They use teachers throughout the whole process. For a couple of activities, I've had the pleasure of being invited to test things out and give feedback. But also once they deploy things, they're always interested in how teachers are using them, how they continue improving them. And so it's through that continued effort that they end up being what I consider by far the best place for resources. So it's great to have Dave to be able to go over some of the particle physics resources with us. Just before turning things over, just to remind you, we're doing this for you, so please ask questions throughout and at the end. Dave's not shy, so feel free to use your microphone, or if you prefer putting things in the chat, I just lost my microphone. Sorry about that.
I'm just getting ready to share the screen. I was just going to take over, Michael.
Okay, so as most of you are aware, a lot of you are aware, I might have some technical difficulties joining you from Ghana, but I think I have a stable enough connection. I apologize in advance if I cut out from time to time. But without further ado, thank you again for joining us. And it's a pleasure to turn things over to you, Dave.
Thanks, Michael. I should have double checked this. It's 1 hour, right?
Yeah.
Okay, good. Just in case you disappear, I want to make sure I don't keep these poor people too long.
And it's 1 hour flexible. So if you go shorter, that's fine. If you're eager to stay on longer, if people keep asking questions, or if you need to cut off right at an hour or anything near there, kind of flexible on that too.
All right. And did I share the right screen? We got the Beyond the Atom stuff. Excellent. Okay, thanks for joining me. What I would like to do is introduce you a little bit to Perimeter and some of the resources that we've created. Michael, thanks for those kind words. I too think that what we are doing here is pretty special, and I think it's the best. And I don't just say that because I've been involved in it. Part of my work involves looking at what other people are producing and seeing what other resources are out there. And we have a really unique blend that we've developed, and I think it's pretty good. So first of all, Perimeter Institute is a theoretical physics institute. So we don't do experiments. We don't have fancy equipment. We have blackboards and a coffee machine. That's what we often tell people, is it's lots of coffee and lots of chalk. You come to our building and you will see some of the top minds in theoretical physics working to solve lots and lots of deep foundational questions. They're looking at things like quantum matter, particle physics, string theory, quantum gravity, all these kinds of things. Each researcher has an area of expertise, but the real focus at Perimeter is collaboration. So it's expected that you will work with people in other groups, and that you will share resources, you will challenge, it's really fun to be at colloquiums or seminars where you know that one person is saying something that the other person cannot agree with, and yet they will share resources. They will stand up and say, have you read this paper? Because I think there's some mathematics in that paper that would help you. And it's really kind of cool to watch this. The building itself is a beautiful place. Because it's theoretical physics, we don't have to spend money on equipment. So we have to spend money on just a really nice facility where people are comfortable and have everything they need to do the work that they do. We also have we're deeply committed to training the next generation of researchers and in doing outreach to the general public. That's been something that's been our signature since we started. In terms of outreach that you would care about for as a teacher, we have a whole suite of in-class resources. And before anybody gets worried about it, they are all free. I am not here to sell you anything. Part of the commitment that Perimeter has to outreach is that they take a big chunk of their budget and they put it into outreach every year. Our resources are developed in collaboration between teachers and researchers. So even this week, we had a great debate going on in my office. There's myself and Ashley, who's another teacher who's on staff right now. And we were kind of not fighting it out, but we were having a really good, intense discussion with a couple of researchers because what we want to do and what they think needs to be done, we aren't agreeing on. And so this is the kind of work that we do on your behalf to make sure that our resources are useful in the classroom. And the researchers are there to make sure that what we produce is correct. So my goal is that you feel confident whenever you look at a Perimeter resource that it is scientifically credible, because there is a senior researcher always signs off on the documents and says, yes, this is good. Couple of other things that you might want to know as a teacher. It's available in English, French, Portuguese, and Spanish. So you can download it in multiple languages. Anything that goes in front of a student, so any worksheet or thing like that, you can download as a Word document as well, so that you can edit it and adapt it to your needs. I write a lot of these resources. I have never used them straight up in my classroom. I always edit them because I'm not writing my lessons. When I produce these resources, I'm trying to create a general lesson, and it's not necessarily mine. So I often will take them and rip them apart and edit them. So we've included that in the design. So please feel free to do that. A couple of things that really stand out for our resources. They are very simple and they are very effective. And they go for a wide range. So we started, our strength is in modern physics. That's what Perimeter does. And so that's where we started. We developed resources for dark matter, general relativity, quantum mechanics, fields, things like that, cosmology. We've also expanded into other regions. So we've done a number of resources with process of science, the nature of science. We've done a climate change resource. And all of them are designed to be fairly low cost. I'm not going to say no cost, because some of them cost some money. We tried to keep the price down. And in cases where we really want to have fancy equipment, let's say, what we've done is we create YouTube videos that you can then watch and show your students. So we set up a little demo. For example, our last resource did some electron diffraction stuff. We don't expect any high school out there has an electron diffraction tube. They are very expensive. So what we did is we just made a really low cost YouTube video that you can access freely, and you can show it to your kids and say, okay, how does an electron diffraction work? That sort of thing. So other than that, our materials are intended to be interactive, inquiry-based, very much hands-on. We really try to stay on top of what the pedagogy experts are saying. So, for example, now we're moving towards doing a lot more stuff with small groups, working at vertical surfaces. The research says this is the best way to teach. We're moving that way. So that's what you'll find in our resources. Another thing, just like what Michael is doing here, where he has a course, we have created now 8 different courses that you can log in. It's about 8 hours of course time, but it's only 3 hours online. The rest you do on your own. So there's some quantum mechanics, there's some astronomy. I have a particle physics course. We have a climate change course, and we're continuing to develop more of them. They seem to be pretty well received. So let's take a look. Let's dive into our particle physics resource. So we have one that is completely dedicated to particle physics, and it's called Remodeling Particle Physics. We just updated it 2 years ago. When we wrote the original one, it was a year before Higgs. So we really felt like it was time to update it and include some stuff for Higgs. And in this resource, so a typical resource has 5 or 6 activities for a classroom. So in this one, we have a scattering experiment. So it's a number of ways of showing Rutherford scattering using balloons, using marbles, using various ways, a very simple way. Activity 2 is taming the particle zoo. We're going to play around with that today. And it has to do with finding patterns in fundamental particles. Activity 3 we're going to look at today as well is bubble chambers, analyzing the bubble chamber images. Activity 4 we're going to look at today, which is analyzing the mass of the Higgs boson. Now, the key here is all of this stuff is at a high school level. And so we are going to simplify some things, but we are also, we're not hiding stuff. We're not pretending. We're getting real data from Atlas and CMS, and we're going to analyze it. And then the 5th one is taking a look at antimatter and Feynman diagrams. We won't have time today to look at that. We also have a couple of other things. One of our other resources is called Contemporary Physics, and it has an activity in it called Detector Physics, where your students can kind of understand the layers in a basic CMS Atlas type detector. So when you take a look, I know you've got people coming from CERN to talk. If your students are excited and want to learn more about that, there's a nice activity that kind of walks them through that. And then we also have a really fun activities we've created called breakout activities. They're essentially escape rooms. So this one is an escape room activity for igniting the orbitron. So it's about particle physics. So it's a really nice review activity to do with your students after you've done particle physics. You can also just grab it and take some of the individual puzzles and use some of the individual puzzles if you want. We do that quite often with our student activities, where we'll just grab one of the puzzles as something that fits somewhere else. So let's take a look at a couple of things. How would I usually introduce this? Well, one of the activities that I really like is called an inquiry cube. And that we've just published a resource, our latest resource called The Nature of Science, and it has this activity in it called the inquiry tube. And in the inquiry cube, you've got a 6-sided cube, and there are names and numbers on each face. And the students, the job is try to figure out the pattern. How are the faces related? And the emphasis is going to be on, okay, once you've built your model, what is on the bottom face? So what we do is we actually put it in front of the students and we say, okay, you can't touch the block. Nobody's allowed to look at what's on the bottom face. So by looking at the opposing faces, can you develop a model of what could be on that bottom face? And it's a really nice activity. There's a guy named Joe Cassette in the States who on his website, he has 4 or 5 different versions of this activity using colors and animal names and shapes and stuff like that. And when I did this in Greece, one of the teachers in Greece, he replaced these with Greek words. So instead of North American names, he put in names that would make sense to his students. Again, that's the kind of thing you would get a Word document. You can put in names that make sense to your students. So the students would work together to try and figure out what is on the face. And the nice thing there is what they're doing is looking for patterns. They're trying to understand what are the patterns I see. And essentially what they're doing is particle physics. Because what do we do in particle physics? We look for patterns. And with those patterns, we make predictions. And that's what we're going to take a look at. So what are the patterns we're going to look at? Well, we're not going to look at cubes. We're going to look at these particles. And particles have certain characteristics that you can use to describe them. They have a spin, they have a charge, an electric charge, they have a strangeness charge, they have a mass, and just for fun, we threw in the date that they were discovered. And now what we're gonna try to do is, and hopefully Michael warned me this might work and might not work based on your technology. We're going to send you out to some breakout rooms. Now, what I need you to do is, before you go to a breakout room, I'm going to give you a link to a Google slide. And I'm going to put it in the chat. And this link will ask you, you'll be prompted to make a copy of the slideshow. And all the slideshow is it's going to have these cards that you see in front of you, but you'll be able to drag them around. Don't run the slideshow, leave it in the edit mode, and that way you can move cards around. I'm going to put you into breakout rooms so that you can talk to each other if you want to. If you don't want to, you can just go to the breakout room and stay quiet and do this yourself. But what I want you to do is, with these cards, I want you to try to put some order to them. Okay, so look for characteristics. How can you organize these cards? And there is one card that's missing. So that's the question mark card. And I would like you and your group, can you describe what should be on that card? Okay, don't try to remember from particle physics. I don't want anybody here trying to remember that page from a textbook. I want you looking just at the patterns here. Okay, so
and I have one question. When they get into their breakout rooms, and they should have the copy they've made of the slide so they can move things around, do you recommend they have one person share their screen and they all work on the same one, or that everyone just,
if they want to, or they can work independently and just talk to each other and say, this is what I'm going to try, and you could try something else on your screen. Right, so they can do it in parallel, or they can all share one screen. Depends on what the group feels.
Perfect. All right, sounds great. How many different rooms do you want?
How many people do we have? Why don't we make 4 rooms? That work? Perfect. Or you want 3 rooms?
No, 4 sounds good, and it'll be approximately 5, like 5.2 people per room. I'll create them now.
Great. That would be awesome. Thank you.
Perfect. So everyone, you should have a link to join the room. Join as soon as you're ready.
But make sure you click on that Google link first. Can you hear my dog in the background?
Moment, but no.
Okay, good.
What's he doing?
She's barking. As always, as soon as you start something where you want quiet. Would it be possible at the end of this also to get a list of sort of who was here today in terms of what countries are represented? That'd be kind of cool for me.
Yeah, of course.
That'd be awesome. All right, so we got a few people who haven't joined, so we'll assume they're hanging in here with us.
And do you feel like popping into any of the rooms to see what's going on, or just hanging out here?
No, I'll just hang out here. I think we'll just give them 5. We'll just give them 5 minutes. So, what's the time now? Yeah, let's give them till 25 after, or something like that. Just gives them. There's a name I recognize.
Which one?
Solomon. He just came in.
Oh, okay, okay.
I think you've done some perimeter stuff, haven't you, Solon? He's frozen.
And
Yeah,
I think he was in before, but then maybe his connection jumped off.
yeah,
He's
we
been,
have that.
I think he's been in most of the sessions. Do you remember where he's from?
He may be from CERN, like he may be an HST guy,
Oh,
uh,
okay.
or think he, I don't think he's an Einstein Plus guy. So I think he's probably an HST and then maybe a couple of workshops. I kind of recognize the name, unless it's somebody else with the same first name. I'm not sure how common that name is.
I'm looking it up. I have him down as being from Iran. So
Yeah,
he could have been on the CERN teacher programs. There was a woman from Iran when I was there.
yeah.
Yeah, I'll see. I should have on my list how many people identified as having attended Einstein Plus. I'll mention some of the names in case any of them are in this session if you're interested.
Well, see, the thing with Einstein Plus is because I do the CERN presentation, I often am not at Einstein Plus, or I just show,
Okay.
or I just show up for a day or two. Like it's. I should have dropped by this year on the Friday, and I didn't because I got back from CERN on Thursday or whatever. So I was like giving myself a day off. But I probably should have dropped by on the Friday just to say hi to people. But that tends to be the reality is that Einstein Plus and HST overlap.
Mm.
And so I always choose, I don't know why, but I always choose HST. I'd rather I'd rather go to Switzerland, I don't know, than hang out here in Waterloo.
Well, it's a good place to be.
All right, let's close up the room. Give him a minute. I think there's
Okay,
a
so I'll give them a 1 minute warning.
yeah.
I think when I go to close, it gives them a 30-second window that they can get out of the
Yeah.
room. It'll be interesting to see what they come up with.
Yeah, we also have this as a Padlet. So it's a nicer it's in a way it's a nicer platform to work in. But I find Padlets are kind of wonky and they're not as accessible as Google Slides. So if I do this and everybody makes a copy of it, it's like giving a handout at a workshop, right? Now everybody's got the Google Slide. So they can go off and do.
And in some ways it serves as a reminder, like if they find it on their drive later, then they'll be
Exactly.
like, oh yeah, I should do that.
Yeah, see, the Padlet is owned by us and it's ours. So you got to log in through us to access it. So it's way more restricted. I prefer the Google Slides because then people can just go and use them.
Well, I think Padlet, you have sharing settings where you can have it, everyone can modify it, but it's harder to make copies of it.
Yeah, and then the problem also is, say you used it this week, at the end of your workshop, everybody has the cards all lined up. So then you have to go through all the Padlets and jumble them all up again. So it's always, or if somebody, deletes something or edits something, you got to go in and you got to clean it up every time. So, all right. So we got 15 seconds. Solomon, how do I know you? Do I know you? You look familiar. No, it's not hearing me. All right, welcome back. Now, I'm just curious, in the chat, does anybody feel brave enough to make a prediction about one aspect of this card? the first person who's really fast can say what spin they think they'll be. Anybody have any ideas what spin it's going to be? 3 halves. There we go.
No.
Dora, I recognize that name. Okay. How about the electric charge? Q. All right, we got a 0. We got a +1. We got a +1, a 0, a 0, a -1. That's great. We got all the choices. Perfect. Okay. How about the strangeness? What do you think in the strangeness? So 0, a -2, a -2, a +1, 0. Okay. So the nice thing here is you haven't had time to really go through this, which is fine. The nice thing here is there are many options for how you organize things. Let me just go through the kind of the simplest way that we could do this. And by the way, whenever I do this with teachers, they really struggle with it because teachers, their idea of organization is a spreadsheet. So teachers want to force everything into columns and rows, and nature does not agree with that. So let's take a look. I have these cards. If I put them into some kind of order, I can make a nice triangle. And what have I done to create this order? Well, I put in the same row, I put all the cards that have the same strangeness. So the bottom row, the strangeness is 0. Then the row above that, the strangeness is -1. Then above that, the strangeness was -2. Then in each column, I put all the ones that have the same charge. So I have +2, +1, 0, -1. And not only am I putting them in a column or a row, but I'm stacking the rows and columns in some sort of order. Now, there is no right way to do this, but putting order to things, this is what scientists do, is they try a whole variety of methods of organization with the hope that a pattern evolves or it shows up. So if we take a look at this, if I see that, okay, there's a nice pattern here, I have the strangeness numbers are decreasing. The charge numbers go from +2 to -1. And I take a look, and the bottom row has 4, and then I've got 3, and then I've got 2, and I've got 1 unknown. So where is it likely that I want to put this unknown? It would make sense that this unknown would be on its own at the top, because now I have 4, 3, 2, 1. That's a nice pattern. Is it guaranteed? Not at all. That may not be right, but let's see. This is how science works, right? We look for patterns, we build a model, and then we make a prediction. And also, you notice here the rows also have increasing mass. So with this prediction, I would say spin 3 halves. That's a gimme. By the way, the activity in the book actually has spin 1 half and spin 0 cards as well. And the first activity the first thing that students do is sort them into those 3 groups. So we're only doing a component of the activity. So if I look at how I organized it, by column, my unknown would have a charge, a Q of -1. It would have a strangeness of -3. It would have a mass of about 1,680 mega electron volts, just by going with the pattern that I see. And in fact, the particle that we have just described is the omega minus particle. And The story goes that Murray Gell-Mann was at the Muon meetings in the late 50s, I believe it was. I'd have to check my dates on that. Actually, this is an easy way to check the date. It was discovered in 64. Okay, so it was probably in 1960 or 1962 at the Muon meetings. The researchers from CERN announced the discovery of the particles in the second row in our chart. And so Murray Gell-Mann was in the room, and he was like, okay, that means 4, 3, 2, 1. So he did this pattern in his head at the back of the presentation. Now, Gell-Mann was also working on this problem previously. He had a ton of mathematics behind it as well. But essentially, at the end of the presentation, they call for questions, and he put his hand up. And as the senior physicist in the room, they gave him the floor. And he stood up and he said, based on what you have said, I predict the existence of a particle that will have a charge of this, strangeness of this, a mass of this. Go find it. And within 2 years, it was found. It was discovered. Now, the interesting thing is there's always good sidelines in stories, right? In science. There was a young Israeli researcher named Nieman, who was also in the room, who also was waving his hand, and he was going to make the exact same prediction, but he gets an asterisk. Murray Gell-Mann gets a Nobel Prize, and Nieman gets a little asterisk in most textbooks saying, oh yeah, there was this other guy who also had a similar prediction. But that's the way it works. So the thing is, just by looking at these simple patterns in the cards, we can make very powerful predictions. And this is what Gell-Mann gets as a Nobel Prize. And the way we have it set up for the kids is we have our kids organize the cards, and the first group to give the teacher the correct description of the Omega Mater's particle gets a Nobel Prize. So we have little printed out Nobel Prizes that the students get. So I don't think any of you get a Nobel Prize today, but that's okay. Now, this is basically the story of the Standard Model. This is how the Standard Model is built. We look for patterns among the particles that we have, and based on those particles, we make predictions about the next generation. What else is missing? What else could be built? And this is how the Standard Model got built. And so essentially in the Taming the Particle Zoo activity that we just started, the next step for the students is actually to introduce them to the up-down strange quarks. And they use those 3 quarks to build all those particles. And they can then start to understand what some of the predictions are, because there are more predictions you can make based on those 3 quarks. There are other particles that should show up that they hadn't observed yet. And so it's a really powerful activity for the students to see how patterning is a key ingredient in scientific exploration. Are there any questions before I go to the next activity? Are there any questions about that Taming the Particle Zoo or the approach that we're taking? I'm going to assume no, so I'm going to keep going then. Feel free to interrupt me. I'm just a high school teacher, so I'm used to being interrupted all day long. Okay, another activity that we do is bubble chamber detector. Michael, has anybody talked about bubble chambers from your other talk?
Yes, Marco just earlier this week on Monday did a whole session on bubble chambers.
Oh, well then I'll just blast through this. So the nice thing,
it can be a good review to check who's remembered since earlier in this week too.
So the nice thing for our perspective as physics teachers is that bubble chambers are rich in basic physics. So even if your curriculum doesn't include teaching Standard Model or teaching particle physics explicitly, almost every high school physics curriculum contains conservation of momentum, conservation of charge, charge moving in a magnetic field. These are fundamental concepts that you can use the bubble chamber as an illustration of these other fundamental concepts. Okay, so just to remind you, bubble chambers, basically we got superheated liquid hydrogen in the majority of them. The liquid, this is always a confusing point for people. The liquid is both the target and the detector. So we have to remember, it's almost like a Copenhagen interpretation here. You always have to keep track of the fact that the medium is involved in the observation. Okay? So what do we get? Charged particles moving through this medium leave a trail. Neutral or stationary particles do not leave a trail. Magnetic fields cause these charged particles to bend. So you either bend to the right or to the left based on your charge and the direction of the magnetic field. And the amount of bending depends on the particle's momentum. So a low momentum particle bends more. A high momentum particle bends less. What are you looking for? You're looking for collisions. In a collision, you have one particle coming out and one particle going in and two particles coming out. What has happened here is the incoming particle has collided with a particle that's in the medium, in the liquid. Another one is a decay, where either a particle just all of a sudden changes or it appears out of nowhere. We can infer neutral particles by using conservation of momentum. So if the bend of a track just changes radically, we can infer that a neutral particle was emitted. And that's conservation of momentum. And then if you want to apply some mathematics, you can actually have your kids, if you've done circular motion, you can actually have your students understand that relationship with momentum and the radius, the curvature. It just comes straight out of, okay, you've got centripetal force, you've got a magnetic force acting here. And you can actually just infer from that the momentum is equal to the charge times the magnetic field times the radius. So there's some really good physics here, high school physics. And that's the neat thing with particle physics, is that you don't have to go into a really, really high depth. You can just stay at the high school level and still do some really interesting physics. So summary, only moving charged particles are evident. Conservation of charge is always maintained. So charge in equals charge out. Momentum is always conserved. The amount of bending can lead to an understanding of the momentum and the charge. And we also have to remember that particles can decay. So let's take a look at a fairly famous image. So this is generated by CERN. They had what's called the 2-meter bubble chamber. So there's a big bubble chamber. So what we have here are kaons that are coming in from the bottom of the page. There's a magnetic field that's directed into the page. So the first question we have is, and this is how it's set up in our activity, is that the students walk through a series of multiple choice questions based on the image. So the kaons that come in are curving slightly to the right. So what's the charge on the kaons? So remember, the magnetic field is heading into the page. So whether you do left-hand rule or right-hand rule, it's your choice. But if you do this, you're going to find that the kaons coming in are negative. So I tend to go with the left-hand rule because I'm right-handed. So it frees up my left hand to trace things out. So I look at these particles. They're all bending slightly to the right, which to me, with my left hand, means my thumb is pointing up. So it's a negative charge. Now, if I look at point P there, at the bottom of the picture, I've circled one interaction called P. I got one trail that splits into two. Now, if I take a look at the bending of the charge that comes out, there's two charges come out. One is bending to the left and one is bending to the right. So the charge that's on the right-hand side, which way is it bending? Well, it's bending to the left, which means that it must have a positive charge. If I keep looking at point P, this doesn't make sense, right? I've got a negative charge that comes in, and I've got two charged particles coming out. So that means that the conservation of charge, I'm missing something because I've got one charge going in and two charges coming out. But what I have to remember is that the target, the liquid nitrogen, is a proton, basically. So you've got a charged particle there. And so what's happened is the kaon has come in and collided with or interacted with a proton that's in the liquid hydrogen. And so you have actually two particles starting. You've got the moving particle and you had a stationary particle that you couldn't see because it wasn't moving. After that interaction, you have a positive and a negative particle moving away. If I take a look at P, I'm going to continue to look at P. There's something wrong with this picture. If I look at this, I've got a particle coming in. When it collides with a stationary particle, it's producing two charged particles that are both veering off to the right. Conservation of momentum would say that if I've got a particle that's going basically vertical on my page, it can't produce two particles going to the right. Something must be produced that goes to the left because my momentum has to be balanced. And so I can infer that a neutral particle has been produced that is moving up and to the left. And that's conservation of momentum. And when I take a look at this, I'm going to skip ahead in my multiple choice questions. Two new particles appear at point Q. Where did they come from? Well, the neutral particle that was produced at P has moved up and to the left and decays into a positive and negative particle. So I've got a photon, I've got a pair production going on there. And these are all just simple, right? This is high school physics. This is conservation of charge, conservation of momentum, and right-hand or left-hand rules. So we're doing some pretty advanced physics. Notice I'm not adding any nomenclature to this. I'm not trying to predict what particle it is. We could, if you've already done that background, if that's a significant part of your curriculum, you could have the students try to figure out what is the actual particle. All I'm asking my students, because that's not in my curriculum, what I ask my students is it a positive charge? Is it a negative charge? Is it neutral? And that's enough of the story for me. And then one other thing is, if we take a look at R, so just downstream of P, you can see that the curvature of the track changes very slightly. And for the curvature to change, using conservation momentum means that a neutral particle must have been emitted. Something is taking momentum away from that particle. So we would say that that particle has decayed into a negative and a neutral particle. So we can actually, and there's several other steps, but I want to get to something with the Higgs boson. So what you can actually get to is telling the whole story here. And notice which image we've got. The taming the particle zoo activity has your students using patterns to predict the existence of the omega minus. And here we have a bubble chamber image in which the omega minus is discovered. Now, actually, the omega minus was discovered at Brookhaven, not at CERN. So there is also an image that the students analyze that is the Brookhaven image. So we have our students walk through both of these images, kind of learning about how they can apply conservation of charge, conservation of momentum, and charges moving in a magnetic field to get this. So it's a really nice, there's places where we can squeeze modern physics into the classic curriculum, and this is one of the places. We all teach conservation of momentum. Particle physics, what is it about? It's all about conservation of momentum. And so instead of having my students look at, billiard table or, a car accident, sure, we look at some of those examples, but I also want to make sure that they know that this is the basic science behind particle physics, so that they can understand that these simple concepts that we teach in high school go somewhere and they are real. And the beautiful thing about physics, and I get all excited about this, is that this small handful of basic concepts like conservation of momentum and conservation of charge and energy, they can be applied on scales that are ridiculous. So we can do an experiment in a classroom and then say, guess what? This same physics explains what we're seeing in astronomy. This same physics explains what we see in particle physics detectors. Because that's the beauty of science, is the scale. It's you can take it anywhere, and that's fun. So that's our bubble chamber activity. And then the last one is discovering the mass of the Higgs. And I want to start with, by the way, all of our resources also come with videos. So this resource, the Beyond the Atom resource, comes with about a 25-minute video that you can watch in full run, or you can cut up pieces. I generally just show little segments of it. This is one of the segments. It's an interview with one of our top particle physicists.
And so when you collide things with lots of energy, what typically happens is that there's lots of particles there, and they will be pair producing new kinds of particles all the time, particles and antiparticles, as long as you have enough energy to produce their mass, which is related to energy through E equals mc squared. In all these collisions, the things that are coming out were not there to start with, and so you're getting a sampling of all possible particles that could be produced at the energies that you have access to, which makes it much more efficient. You have to choose the initial thing carefully to have the right ingredients, so you can collide almost anything at high enough energies, and you're going to get everything out.
So that's Cliff Burgess. He's one of my favorite researchers at Perimeter. He calls it like it is, and he's had a lot of fun at the expense of the LHC theorists like John Ellis, because there was most of the school of thought at CERN. There were a lot of people who were really counting on supersymmetry showing up, and it hasn't. And Cliff never thought it would. So he told me about how he goes to meetings after the LHC started to show really clear evidence that it's not happening, and he'd walk into the meetings and go, "Why are you guys all so sad?" and he kind of teased them because their theories weren't working. But the key with the statement that he made that I think is really important is that what we're doing in particle physics is, if we put enough energy into a scenario, we get everything that could possibly be created under that level of energy. So the rules of quantum mechanics, there are all sorts of conservation rules and all sorts of stipulations. But essentially, what we're doing at the LHC or at FermiLab or at SLAC or at DESI, all these different particle colliders, we're shoving a whole bunch of energy in and seeing what we can create with that energy. And it's a really beautiful example of E equals mc squared. So if you're teaching energy mass equivalence, this particle physics is a beautiful example of it, because this is what we're doing. We're taking energy and we are converting, if you will. I don't like think of converting energy, but the energy of motion is being put into that collision, and the energy as mass is coming out. Now, there's all sorts of other constraints. Quantum mechanics does not say anything can happen. Quantum mechanics is full of rules. If you remember your quantum mechanics from undergraduate days, it's a course full of rules. So whenever people sort of outside physics say, well, quantum mechanics says anything can happen, they have not taken a quantum mechanics course. There are all sorts of constraints, and we know that. So when we collide things together, there are really clear pathways for what could be created. Okay? And so CERN, when they smash these antiprotons together, they know all the possibilities of what could come out. And quantum mechanics, the standard model, also predicts how much of each they should expect statistically. So we have a really good idea of what's going on. Now, the first thing we do in a collision is you look for what's called the transverse momentum. So that's the momentum that's coming out of this collision. If your transverse momentum is non-zero, you got two options. Okay? You either missed a particle. In the case of the top quark, for example, in our first edition of this resource, we didn't have the activity for the Higgs. We had finding the mass of the top quark. You can still find that on our website as an individual lesson called Finding the Top Quark. And in the top quark analysis, we did expect for a neutrino to be created. But that's in the predictions. That's according to the constraints. We thought there would be a neutrino. So when the momentum didn't add up the way we thought it did, we said, okay, there's a neutrino there. That's the momentum of the neutrino. In the case of the Higgs, we didn't expect a neutrino. So if the transverse momentum is non-zero, that says that the Higgs had momentum initially. And that's because when you create a Higgs, you're not creating a Higgs pair. You can create the Higgs. And so it has momentum. And so that's what we're going to look at. We're going to use some constraints on this. Now, I'm going to invoke a little bit of relativity here. Some high schools have this and some don't. So if I'm teaching my students to do this analysis, I have to walk through this with them. But I like it, so I want to make sure they know this. So in special relativity, the total energy of a particle is a combination of two things. It's momentum, it's the relativistic momentum and the mass. And by the way, this is something that the CERN people beat into me. There is no such thing as relativistic mass. This idea that things get heavier as they go faster is not valid. The mass is invariant. It never changes. And that's important, actually, for our analysis. So as we put more and more energy into a system, this equation on the screen is what tells you where the energy goes. And it's not going into the mass. The mass does not change. That term does not change. All of the energy that we pump into the LHC is going into the momentum term. We are increasing the momentum of the particle. We are not changing its mass. And so when we get to really high speeds or high energies, the mass term becomes negligible, right? So what's the mass of a proton? It's like 981. So it's not even a giga electron volt. And yet you're looking at LHC, at collisions above 7 tera electron volts. So these, the mass term becomes negligible. You don't need to worry about it. And this whole equation simplifies and says that the energy of your system can be, to a good approximation, given just by the momentum of the particles. So in a total collision, when we look at a collision, what we can do to figure out the energy of that collision is simply add the magnitudes of the momentum vectors. So that's how we determine the momentum of the initial particle. We can simply say, what's the total momentum coming out of the collision? That allows us to infer how much momentum went into the collision. Then we can also use the momentum vectors to tell us the total energy of the system. And then all we have to do is subtract one from the other. So this is pretty straightforward. So let's take a look at how a high school student could do this. Once they have that background, that's a little bit of background that most high school students wouldn't have. But let's understand what's going to go on. So this is a picture from Atlas of a real collision. Now, it's a special collision. Okay, we need to be aware of that. This is a collision where the four principal components are all in one plane. Okay, that's a special one. But guess what? They do billions of collisions. They've got some special ones available for us. So we're going to take a look at this special slice, and we're going to analyze these four momentum vectors. And any high school student can do this. And we can also do this with CMS. So the way we have this set up in our activity is you have half your class do CMS and half your class do Atlas. And then they can compare, just like CERN does, where CMS and Atlas do their independent analysis, and then they come together and say, okay, here's our average, what's your average? And if they both had the same number, we have a press conference and we shut down the internet. It's great. So how does this work? I'm just going to run through one because we're almost out of time. So basically, you've got this CMS, you've got four vectors because you have four particles that come out. We're just looking at one channel. So you have your students break the vectors into their components. They add up those components to get a total X and Y component for the particle. So then they can get their net momentum. So this is the momentum of the Higgs that came into the collision. Then we say, okay, so we've got our initial momentum. Now let's figure out the total energy. For total energy, all I have to do is add together the four magnitudes. And that gives me my total energy for the system. And then I rearrange Einstein's equation. I take my energy, I subtract my momentum, I square root it. Bob's your uncle, 122 giga-electron volts. Now that's pretty good, considering CERN spent billions and billions and billions of euros to get 125. We did all right. And guess what? If we do it with Atlas, I'm just gonna fly through it because we're out of time. We get the same number. So your students will understand the idea of why do we have to have two detectors at CERN? Well, we need two detectors to verify independently that the physics is correct. One last thing I want to show you is if you like to have fun with your students and do escape rooms, we have one called Igniting the Orbitron, where basically, I believe it was Fermi who came up with this idea. Just for fun, he said, we should put a particle accelerator in orbit around the Earth because then we get a huge radius and we could really ramp that thing up. And so that's the premise, is that we build a particle accelerator in orbit. Some nice thing here, what we do is each clue we associate with a different lab from around the world. So Super K, SLAC, CERN, I think Ice Cube down in Antarctica. So the idea is also to show your students that particle physics is this real international affair, and there's input from all different countries. Our resources, again, they're free. You can download them at our website. Now we use Shopify, which is our platform. It looks like a store, but everything is free. So you'll have to make an account and you'll check out and add things to your basket, but all the price tags are zero. And we have resources, we have posters, we have breakout activities, lots of things. You take some time. We have well over 30 different resources now, spanning from middle school all the way to senior high school. There's my email. Feel free to send me any questions you have or ideas or whatever. We are here to help you as a classroom teacher. I really appreciate you taking time out of your busy schedule to spend with me, but I hope this has been a useful time.
That's been really great. Thank you, Dave. And I'm guessing you're happy to answer any questions if people have questions before we say goodbye.
Yeah, sure.
Perfect. And just as to give people a moment to think of questions, if you have any you haven't thought of yet, just to remind people, coming up next week, we'll have 2 more sessions. Tuesdays will be with Jesus Puerta Pelayo, who's the head of outreach at Ciemat in Madrid, and he's on the CMS experiment. So he'll be going into details on the Muon telescopes and the history of gas detection. He was telling me yesterday, texting me, it'll be kind of like a baby book of pictures of CMS from when it started, because he was on it while they were planning it like 10 or 15 years before they actually built the thing. So it'll be a cool perspective of that. And then I'm really excited on Thursday, there'll be Federico Andrioletti, who I asked if he wants to say hi, and he said, yeah, sure, why not? And he'll be leading Thursday's session with a homemade radon detector. So I'm really excited to see him. And do you feel like saying hi and say, come to my session, Federico?
Yes, hi everybody. Thank you, Dave, for your presentation. Next week, I will show to the audience an homemade ion chamber. And it's very useful for students to understand how the detector works and actually to gather some data about the radon gas and its behavior in our lives. And I hope that it will be a useful experience for students. And actually, I have 2 students that are working on some example and using the ion chamber for radon in their house and in their own environment. So see you next week.
Thank you, Federico. And having him being able to show that, and right after Jesus shows how a gas detector works on the LHC, is one of my goals for this course, bringing together both teachers and scientists with things that are top level science and things that you should be able to do in your classroom. So that was one of my goals. And next week, I'm looking forward to very much. I think that probably gave time for people to think of questions for Dave. So hopefully someone's thought of something you want to ask him just before we end the session. And any questions either in the chat or using your microphone?
Hello, I would like to ask something.
Perfect.
Thank you, Dave, for excellent presentation. I really appreciate all the resources you and your colleagues done for teachers. And my question is about the CMS and Atlas verification of data. So when in CMS and Atlas smashed different protons, how they can verify that they have the same result in Atlas CMS?
Well, the basic thing in all of these particle physics is it's statistical analysis of millions of collisions. So it's never about one collision. It's always about, you have 2 independent detectors that are observing millions and millions of collisions. And they create a profile of how many of each particle they basically are detecting. And that tells them, you know, and basically the discovery of the Higgs was that there was an excess of particles that were created from a certain mass. And both Atlas and CMS detected this this excess of particles. And so they created a statistical analysis that said, after we've observed a certain number of collisions, we are observing that there must be something at 125 giga electron volts, because we're detecting all these other particles that add up to 125. And so that's essentially the I'm cutting a few corners on the analysis here, but that's essentially what they do is they find that they detect all these particles, and then they say, okay, where did these particles come from? And okay, that came from a top quark. Well, we know about the top quark, ignore it. Okay, but then they had a whole bunch of particles that they were detecting that added up to 125 giga electron volts. And so that told them that they were creating a particle that was 125 giga electron volts and then was decaying. And both Atlas and CMS, they used what were called different channels. So in what we did today, we only looked at one channel. We looked at the channel where there were 2 positrons and 2 electrons created. There's another channel that's 2 photons that are created. There's another channel where it's W bosons are created. There's 6 different channels. And what that basically does is gives you a statistical profile for what are the odds that you are going to measure this many electrons of this kind of momentum. And that's what leads to the discovery of a particle. And that's where they start talking about 5 sigma, that's a statistical analysis that says, what are the odds of finding this many particles that add up to 125? And when they said, okay, the odds are really, really, really low, that this is noise, they said, okay, we've discovered something.
Thanks very much.
No problem.
That was a good question. Does anyone have anything else they want to ask? And keep in mind, you can always email Dave or email me if it's something I can handle, or I can refer you to someone to answer as well.
And if you're going to use any of our resources and you have questions about how to do it, for sure, email me and say, okay, I've got some questions here. I want your experience to be positive. I know these resources work well in classrooms. I have no doubt. I have no hesitation recommending them, because I've seen them work in thousands of classrooms around the world.
And I'm assuming, Dave, you're like me, where if you hear from someone who's using something, even if they don't need your help, it's always just nice to hear that your stuff is being used other places.
Oh, we love it. We love it. And if you say, hey, you know what I did? I tried this and it worked really well. We like the particle physics resource that's available now is the 2nd edition. So we made a bunch of tweaks. We corrected things and added things as we heard from teachers. So we're now old enough. We've been around for almost 25 years now. So we're now at that age where we're going back to our original resources and saying, how can we improve them? How can we do these better? So we've already rewritten 2 or 3 of them based on teacher feedback. So yeah, we love teacher feedback. I can't be in every classroom in the world.
And like I've mentioned repeatedly, Perimeter is the best place I can think of actually listening to teachers. And if you say, I tried this, it worked well this way, or this part of it didn't work, they're actually really keen to say, okay, tell me more about that. How can we make this better? And there's a lot of other people doing outreach stuff. If you try and say how it worked, if it's not just raving about it, they'll kind of shut off and won't be interested. So please do get in touch with Dave, because they are looking, well, they always take on board use cases, feedback, things like that.
And in the summer, we run a teacher camp called Einstein Plus. I should probably put a plug in for it. Some of you,
I want to look up the link quick for that.
Yeah, some of you have, I recognize your names from the CERN HST camp. So Einstein Plus is our version of that. It's a 1-week camp where we bring teachers from around the world together to talk about how to teach physics. And it'll be the time of your life. Jeff and I argue over whose camp is better. HST or Einstein Plus, but we have better food and we have free coffee. You don't have to pay for the coffee at Perimeter, so we win. Excellent. That's great to hear, Dora. So she's using the cubes translated into Greek. We're trying to figure out how to get them translated into what's called a Nuktatuk, which is the language of the far north. And it's all syllabic, so it's weird symbols. So we're trying to find somebody who can do that translation for us.
And I think that brings the questions and comments to an end. So I'll conclude by again thanking you again, Dave, and thanking everyone for joining us for this. And I hope to see everyone on Tuesday for Jesus' session, and especially on Thursday for Federico's session.